thank you, and thanks to the organizers for this is my favorite kind of workshop where we just get to talk about physics and be total geeks, and so I apologize in advance if I geek out at you, but I'm so excited about some of this stuff. So it's lovely to be here. I want to first of all begin by acknowledging that this is actually not my work. Oh, this is a non-reflective screen. Was there a stick? Marco, do you have? Can I borrow your mechanical system? Mechanical. This is brilliant. So, weather forecast. Yeah. So this is work that's actually been led by my colleague Oleg, but I really want to talk to you about it, and it's funded by this Australian Centre of Excellence Fleet, and then we have a number of excellent collaborators in Bochum and Cambridge. So my group's got a number of projects. We're working on very fast silicon hole spin qubits where we're running them at 500 megahertz and doing single spin manipulation in planar silicon MOS structures in collaboration with IMEC and Dirac, a startup in Australia. And that's a lot of fun, and there's lots of interesting physics there. We're working on topological systems, looking at, for example, chiral spin gaps in hole quantum wires. And again, we're using holes because they have very, very strong spin-orbit interactions, so we can create topological response quite easily. We're having some fun just putting the flow back into electricity and looking actually that when electricity flows through electronic devices, it flows like water. At high school, you were told that electricity is just like water. It flows like water. Well, water should have whirlpools and vorticity. Does electricity? And the answer is yes, it does. And so Marco, again, this is following on from work that Marco had done about a decade ago, and it took me 5 years to understand why he was so excited about it. And what I'm going to talk today is artificial quantum matter and some of the work we've been doing in this area. So first of all, I have to acknowledge that this is really work done by my colleague Oleg, who can't be here because he's teaching and I'm not, and Daisy Wang, who's an amazing experimentalist. And we've got Oleg Sushkov and Zeb Krix, who are fantastic theory support, and then wafers from Dave Ritchie, Andreas Wieck, and Werner Wegscheider. So what I'm going to talk to you about today is how you can make synthetic quantum matter in superlattices. So I'll talk a little bit about motivation of superlattices and Moiré, our new approach to making bands, how we demonstrate a precursor to band structure, then actually how we generate a completely new band structure, and then right at the end, just some notes on flat bands and topological, non-trivial insulators. So one motivation for this is quantum simulation, that if you've got a system, you could build an array of, for example, quantum dots or atoms and use that to simulate the properties of a complicated system. And there's quite a lot of interest in doing that. And of course, another one is that if you can engineer the positions of atoms arbitrarily, you can make artificial quantum matter. And there's this very nice review by this reprobate, Marco Pollini, talking about different approaches to making artificial, and again, 10 years afterwards, I'm following on from him. Different approaches using cold atoms, STM, and so on. And one of the interesting approaches to making artificial quantum matter is to use solid state. And the reason it's interesting is here, that this is, despite cold atoms being called cold atoms, they're not very cold. In the following sense, that the Fermi temperature in cold atoms is comparable to the intersite energy. So it's difficult to get to the low temperature regime. Whereas in condensed matter, the Fermi temperature is 0.1 Kelvin, you can have U 3 or 4 orders of magnitude larger. So you can really reach the low temperature regime. If you want to do that, what you would want to do is you would want to create synthetic matter with a lattice constant which should be less than 100 nanometers, because that defines your energy scales. Obviously, the mean free path of electrons should be longer than your lattice constant, otherwise it's just disordered. So you need low disorder. Your lattice, you should be able to create a periodic lattice, just like nature does. And you need strong modulation. If you just have a very weak modulation, the electrons don't notice there's a lattice. So those are kind of the experimental requirements for making artificial lattices. And, well, I think we all know that moire superlattices, by twisting two materials with respect to each other in these van der Waals materials, you can create a periodic lattice. And then in that periodic lattice, you can form flat bands, and you get all sorts of exotic physics occurring. There are some opportunities here in that when you're twisting these materials, getting uniform twist angle and not having twist angle disorder is slightly non-trivial. Particularly for magic angle, you have to keep the twist angle very uniform. And tuning the potential that you're creating is not so easy, because that's really set by the two sheets that you're twisting with respect to each other. And of course, you've got a fixed symmetry. You're stuck with a triangular lattice because you're starting with triangular lattice materials. What you could try and do is take that graphene and pattern an artificial lattice into it. And so there have been attempts using chemical etching to make artificial lattices inside graphene, or electrostatic gating to make artificial lattices inside graphene. Another way of doing it is to take conventional semiconductors, and on a conventional semiconductor such as gallium arsenide also put an artificial lattice, and then look at the electronic transport of electrons through that artificial lattice. And in all these previous studies, what you can see is that you get a weak modulation of the electron gas, and so that causes a small correction to the quantum transport properties. But when you try and get a strong modulation, the disorder kills you, and you just end up with a disordered insulator. Optical studies have been more promising, and you do see in optical studies you can etch down and create a strong modulation. But and there is evidence then of forming Dirac-like bands by creating a honeycomb lattice on a two-dimensional system, but the modulation can't be tuned. So you're sort of stuck with, once you've made the sample, that's it. So we wanted a new, more flexible approach to making artificial bands, and so that's what I want to talk about next. So our approach is just, let's use transistors. The industry is very good at these. We know we've been working on transistors for many years. So we have a high mobility two-dimensional electron system in gallium arsenide. We have a gate into which we pattern a periodic lattice, and then a dielectric, and then another gate on top. And with the combination of these two gates allows us to change the strength of the lattice potential and the chemical potential independently. So we can go from having very weak modulation to very strong modulation. And we can create lattice constant of about 100 nanometers. The mean free path is much, much larger than the lattice constant, so we're in the low disorder regime. We make the lattice very regular, and we can get very strong modulation where this potential is much larger than the chemical potential. And of course, because we're making it with electron beam lithography, we can make any lattice shape you want. We're going to concentrate today just on triangular honeycomb lattice. So to compare with other solid-state approaches, this is kind of the disorder on this axis. You want the mobility to be as large as possible after you've patterned it. You want the lattice constant as small as possible. And this is the quantum regime. If you're in this regime, you'll see new physics. If you're in this regime, essentially you're not going to notice that you've put a lattice on top. And so these were the early experiments on etched gallium arsenide systems, and they just about got into the quantum regime. These are experiments on etched graphene systems, and they never really got into the quantum regime. And then we're kind of up here. So we've managed to get the disorder down and keep the mobility. And compared to moire graphene, you could look at, say, the number of bands that you can tune the chemical potential through as a function of the normalized modulation strength. Moire graphene, you can kind of go through about one band. The modulation is about a few times the Fermi energy. If you etch gallium arsenide, you can get stronger modulation, but you're still not very tunable. Graphene pattern substrates, you can get tunability, but at the cost you don't have strong modulation, and then we can pretty much span everything on that phase diagram. So what do you need to make bands? Well, here's an electron in free space, E versus K. If I then put a periodic modulation on it, so this is essentially the honeycomb modulation, triangular modulation, what I'll do is I'll just create copies of this band. And when I create those copies, I end up with this band structure. But there's no anti-crossings in the band because the potential at U is 0. As I turn U up, what happens is this band here, this free parabolic band, now gets little anti-crossings. And I form now my, this is now my Brion zone. And as I turn, but here still I don't have any band gaps. So if you were to do any transport measurements, you would just see a continuum of states. What you have to do is you have to keep turning the modulation potential up, so making the potential stronger and stronger, until it's comparable to the Fermi energy. And at that point, you start to get individual bands. You see you get a Dirac point here. You haven't quite got a band gap. If you turn the modulation up even a bit more, then you get a band gap. You get Dirac bands down at the bottom, a band gap, then a flat band. And this is, of course, a Kagome band structure up the top. So if you could do this, you could tune from Dirac physics to flat band physics to Kagome physics all in one go. It's just not very easy to do it. So this was 6 years ago. This was our first generation of samples, and they were just too disordered. 4 years ago, this was our second generation of samples. We got the uniformity of the lattice, really improved it. They were still too disordered. You're really susceptible to disorder. We did a lot of numerical calculations to show how disorder hurts. And then our third generation of devices that sort of started working about 2 years ago, now we can really make large lattices, multiple gate layers, and finally we can get very high mobility. And one of the very good quality samples. And one of the trick was you have to get the two-dimensional electron system very close to the surface, but keep a high mobility. So these 2D electron systems are 25 nanometers or 30 nanometers below the surface, but still very high mobility. And so, how long do I have?
As long as you want, because I really like this.
Okay, well, I'll finish tomorrow. All right. So let me do a precursor to band structure, which is what everyone has been doing for the last 20 years. And so that means I'm going to create a weak modulation. So what would you see if you took a two-dimensional electron system and you put a weak modulation on it? Well, so this is the same story I said before. This is what I teach in third-year solid-state physics. The dashed line is just E versus K for an electron in free space. And then when you put a weak modulation on it, you open up bands, and you know from teaching third-year solid-state physics that the size of the gap that you open up is proportional to the size of the modulation strength, right? It's the first harmonic. And then this gap is the second harmonic of that potential, and so on. And if you've got an isotropic system, then if I take a cut at a particular energy in the bands, I end up with an isotropic Fermi surface. If I now increase the modulation, what happens is my parabolic band here gets some small structure on it. I don't open up band gaps yet, but I get a small anti-crossing here. And so I get copies of this first Fermi surface happening again here at K plus G, and then again at K plus 2G, and again at K plus 3G. And that's how we teach the origins of band structure to undergraduates. So what happens then is my Fermi surface, here's my first Fermi, my first parabolic band, and then it gets repeated one inverse lattice constant away, and then it gets repeated another inverse lattice constant away. And so I get a series of Fermi surfaces like this. And if I take a cut through these, I will end up with Fermi surfaces like this and new shapes. Or if I draw it for a honeycomb lattice, this is Kx and Ky. Here is my original Fermi surface, and then here's a copy outside the first Brion zone, and then the second Brion zones out here, and so on. And so what you might expect to see is some signatures in the magnetotransport of these additional replica Fermi surfaces. And so if you look at, this is the magnetoresistance as a function of magnetic field, you see Shubnikov de Haas oscillations, but superimposed on those Shubnikov de Haas oscillations is an additional frequency. And you can do this for a whole bunch of different electron densities, and what you can see kind of beating patterns in there due to the multiple frequencies. And whenever you see multiple frequencies, the first thing you do as an experimentalist is you take a Fourier transform. And so this is the Fourier transform as a function of electron density. And you can see that there's a whole series of different frequencies coming out in the magnetotransport. And these are really kind of simple to understand. The most obvious one is the original unperturbed Fermi surface. So we call this one A0. So this just increases linearly with the electron density. So that's my original Fermi surface. Then there's this Fermi surface here, which is caused by the intersection of the first two Fermi surfaces where they're repeated across. And that has a much smaller frequency. That's this line here. And these solid lines are fits just to a calculation of, knowing the periodicity of the lattice. That's the only parameter we have. And the density, I can immediately calculate what these frequencies should be, and so the solid lines are those calculations. And then I could have a Fermi surface that looks like this. And that will be 2A0 minus A1. And again, that agrees beautifully with experiment. So what I'm doing is I'm scattering my electrons off this periodic potential. You can think of it as kind of a weak scattering. I haven't yet created a band structure. If we turn up the modulation a little bit, we have these multiple different Fermi surfaces. But then we get, in addition, 2 extra frequencies in the Fourier transform. And this caused us some consternation until we realized that what those frequencies are is here is my artificial Fermi surface, and here is my lattice. And I'm scattering my artificial Fermi surface off the periodic lattice. So I've gone from, actually I have it here. I've gone from having this circular Fermi surface to having this A1 Fermi surface. When I go into reciprocal space, or reciprocal space back to real space, you rotate by 90 degrees. This is the real space electron trajectory, and this is the crystal lattice that I've imposed. And whenever that real space electron trajectory fits nicely inside the artificial lattice, I get a minimum in the resistance, and therefore I get these additional frequencies. This can only happen for the honeycomb lattice because I've got this symmetry of the direction of the lattice and this direction of the lattice. So what I'm doing now is, why this is nice, is these 2 extra lines here are classical commensurability oscillations of this new Fermi surface A1, as opposed to commensurability oscillations that we saw previously of that original Fermi surface A0. So I'm scattering a new Fermi surface off an artificial 2D lattice. So I would say that's evidence that I've created a new Fermi surface. But it is not evidence that I've created a new electronic band structure. So that's what I'd like to do next. I'd like to create a new band structure. So we keep the same devices. Before we looked, essentially we had a weak potential, the electrons traveling along are scattering off this weak potential. Now what we want to do is go to a strong potential. And so our band structure goes from not having any gaps and being basically free electron-like with some structure in it to we want to see if we can form these Dirac points, and if we make the modulation strong enough, we should open up a gap and form a flat band. And so these are the calculations of what the band structure should look like for the sort of voltages that we can apply in experiment. So the first thing I'd like to show you is that we can turn electrons into holes. So let me take my 2-dimensional electron system and start with no modulation at all. Then the Hall voltage as a function of magnetic field is a straight line. Okay, we all know this. And the slope of that straight line tells me the carrier density and the carrier type. So that slope is electrons. So I'm going to, and if I take the derivative of that slope and plot it as a color, it's positive. So everywhere here, for all of these gate voltages and all of these magnetic fields, this is behaving like electrons. That's no surprise. Now what I'm going to do is turn up the modulation a little bit. And when I turn up the modulation, my Hall voltage, instead of being a straight line as a function of magnetic field, kind of goes completely flat around zero magnetic field. And if I turn up the modulation a little bit more, the Hall voltage actually changes sign around zero magnetic field. That means here I had electrons. Here, this Hall voltage, it's changed sign. I've changed my electrons into holes. And this is exactly what I expect. Down here, I have electrons. Up here, I should have holes. So what would be really nice is not only to change electrons into holes, but actually to go electrons, then holes, then back to electrons, then back to holes, and follow that sequence of changing of the band curvature as I change the chemical potential and relate it to the calculated band structure. And so what is plotted here is increasing density on the y-axis, magnetic field on the x-axis. The color code blue is that slope that we had before. That was electrons. Red, the color means holes. And here we go. Electrons, holes, electrons, holes, electrons. And we can relate that to this band structure. Electrons here, holes here, electrons here, holes up here. So we can follow, in this artificial crystal, switching from electrons to holes and relate it directly to the calculated band structure. And the only parameter we have is the strength of the modulation potential. So that's really nice. We can calculate for that strength of the modulation potential what the electronic charge distribution looks like. And no surprise, it looks like a honeycomb lattice. We get the potential modulation. Peak-to-peak potential modulation is about 4 millielectron volts. Our Fermi energy is about 3 millielectron volts, or 1.5 millielectron volts. And will you say, if I've got a Dirac point here, shouldn't I have a peak in the resistance where I form a Dirac point? This is a line cut at zero magnetic field, so this is the sweeping the chemical potential. This is the resistance. As I come down and approach the Dirac point, there is a peak in the resistance that happens exactly when the chemical potential is there. So, I don't know. That peak occurs exactly where we predict the Dirac peak point to be. And we get a band disorder of about 0.2 millielectron volts compared to a band width of about 1 millielectron volt. So I think what's nice about this is if we believe this, and I have no reason not to, we've taken ordinary electrons in gallium arsenide, which is a zinc blend cubic crystal, and we've imposed a triangular lattice. So we've got a completely different lattice symmetry. We've changed the electrons from being electrons into holes. We've changed them from being massive electrons to massless Dirac particles. I think that's kind of nice. But wouldn't it be nice if we could make this band flat and maybe do some flat band physics? And so to do that, we need to increase the modulation strength. That's just a matter of increasing the gate voltage. We can do that. So we increase the gate voltage. The peak-to-peak modulation goes from 4 millielectron volts to 9 millielectron volts. And if we don't look at these two bands, because nothing interesting is happening here, we want to see what's happening with the flat band. If you just calculate the charge distribution for these two bands here, you get this charge distribution, which is, of course, a Kagome lattice, which is no surprise because this is the band structure of a Kagome lattice. So we can tune from honeycomb to Kagome charge distributions. And this is where it gets really cool. If you have a lattice, then if I thread one magnetic flux through that lattice, everything, to quote my predecessor once again, everything should be gauge invariant. So whatever the resistance is, if I thread one magnetic flux quantum through it, I should get the same resistance. So the resistance should be periodic in magnetic flux per unit cell. And this is the magnetoresistance as a function of magnetic field, and you see these periodic oscillations. And this has been known since 1964, and Zach put it down as magnetic breakdown of crystal structure. So this is like the Hofstadter butterfly, but it's the integer version of the Hofstadter butterfly. So for us, going from 0 magnetic field to 2 Tesla is equivalent to going to 320,000 Tesla in graphene, or over 100 Tesla in magic angle graphene. We're threading so many flux quanta through this lattice that we're completely breaking down the original crystal structure. And if you look at the Hall voltage as a function of flux per unit cell, this is the Hall voltage plotted here as a function of flux per unit cell, and then you just increase the chemical potential, so just by sweeping the gate voltage, you can see these periodic oscillations here. You can see these kind of stripes here, and the system just shows these periodic oscillations as I gradually thread more and more flux through per unit cell. You can see it a bit more clearly if I just take the derivative of the Hall voltage as a function of magnetic field. And again, I start down here, and then here I'm plotting the derivative as a function of magnetic field, and I'm just going to sweep the chemical potential up through. And as I sweep the chemical potential, you can just see these beautiful periodic oscillations as I'm threading the flux through the unit cell. And what's really nice about this is then I can say, okay, well, when I go from this point here to this point here, that's 1 flux per unit cell. I know what my lattice constant was because I built the sample, or Daisy built the sample. So I've got an absolute calibration. The X periodicity of these oscillations is the number of electrons per band. The number of flux quanta per band. And the Y periodicity is the, so that's the periodicity. This way I've got my X and Y the wrong way around. The Y periodicity is going from here to here, is I'm filling 1 band. So that's this periodicity. So I've got an absolute measure between my electrical gate voltage that I'm applying and the number of bands I've filled. So I know exactly where I am at any point on the band structure. And then what you see is in the oscillations, there's this kind of phase shift here, and that just seems to happen at the same point as we go from a honeycomb lattice down here to a Kagome lattice up here. We don't quite understand why there's a phase shift, but it doesn't appear in single particle calculations, but there you go. Well, you might ask, this is all wonderful, but we've done mesoscopic physics before, and we know that if you make any device, you can get any result you want if you measure enough of them. So you've calculated the band structure. You know what the answer should be. What you did was you just made 100 devices until one of those devices showed the thing you were looking for, and then you went for fame and glory. Okay, so here is the data that I just showed you. It was on a 30 nanometer deep wafer, or 37 nanometer deep wafer. It's got an electromobility of about 600,000, and that was with a 120 nanometer lattice constant. It's got a 10 micron area. And so this is the Hall voltage on the z-axis. The y-axis is the chemical potential, and the x-axis is the magnetic field. So this is the periodic changing of the sign of the Hall voltage. This is a completely separate wafer. It's a different depth, a different electromobility. The lattice constant is different. And yet these pictures look really, really similar. And if you take this data and normalize it for the change in lattice constant, you can just move it straight over and plop it on top of the other data set. So these are 2 completely different lattices, completely different wafers. In mesoscopic physics, I never see anything like this happen. And so we've measured something like 8 or 10 of these devices now, and all of them show the same behavior. All of them show the same band filling. It's really nice. So we've got a way of making artificial bands. We've demonstrated it with triangular lattices, but I'm sure we could demonstrate it with square lattices, Lieb lattices, any kind of lattice you want, as long as it's 2-dimensional. Could we make flat bands, and could we artificially create correlated states? So this is now, we go to the strongest possible modulation, and I'm going to sweep the chemical potential and just look at the resistance. And at some point, there's a huge peak in the resistance, and then it drops away again. Even at that resistance point, I've got the same flux periodicity as the lattice, which means that that insulator has the electrons in the insulator know about the lattice that I put down. It's not a disordered insulator. The other thing is that this insulator is killed both at high electron densities, well, if it's a disordered insulator and you throw enough electrons in, you'll kill the insulator, but also at low electron densities. So that really argues against Anderson localization. It only happens exactly when we predict the flat band to occur. If we take the width of that resistance peak, it's about 24 millivolts in gate voltage, which from our previous calibrations we know corresponds to exactly one band of electrons. It's not consistent with a single particle band gap, which would take about 1 millivolt in electrons. It's 20 times too big. So that strongly suggests that whatever this insulator is, it's coming from the flat band. So we're very interested to continue understanding that. And from the theory, we know that for the potentials that match our data, U on site divided by T is about 50. So we're very much in the strong correlation regime. So sorry for running so long and keeping everyone away from lunch. It is now possible to make artificial band structure. You can tune the Fermi energy. You can tune the on-site Coulomb energy. You can turn electrons into holes. You can fill Dirac bands. You can make a transition from Dirac to Kagome lattices. You can create band gaps. We have observed a non-trivial insulator. And it is possible to go to do all sorts of new physics as well. So, thank you. And in particular, I'd like to thank my colleagues, Oleg Klochan and Daisy Wang.